Here I'm actually going to solve the differential equation that we were just analyzing. That differential equation was one that modeled the growth of a deer population, and it had this form. So I'm going to solve this one, although it's not probably something that it's probably not something you'd be required to do with this particular type of differential equation, just because it's a long problem. But it'll at least connect why we did partial fractions. It was for this particular reason, and it'll remind you of some of the basic principles of solving a differential equation. So first thing we need to do is separate the variables. So what I would like to do is what I usually do is I put the p in the 500 minus p with the dp, and I leave the constant over here with the dt. So then we take the antiderivative of both sides. Now the right side's easy. It's just 0.0008t plus a c. It's this guy here that's going to require partial fraction decomposition. So I'm going to say 1 over p times 500 minus p. Notice that's the denominator is factored into distinct linear factors, so I can write that as a over p plus b over 500 minus p. And then we can get our common denominator. And we end up getting 1 equals a times 500 minus p plus bp. And we choose convenient values, so when p equals 0, then we get that a is 1 over 500. I'm kind of rushing through that, but I think you can see that pretty easily. And when p is 500, b is 1 over 500. Okay, so now what? We can actually go back to our differential equation here that I'm going to, or the integral rather, that I'm going to highlight in blue there. I'm going to make another column. So now we know that that can be written as the integral of 1 over 500 divided by p plus 1 over 500 I'm going to zoom in on this. 1 over 500 divided by 500 minus p. And that's equal to 0.0008t plus c. Okay, the antiderivative of this guy on the left is natural log, 1 over 500, natural log of the absolute value of p. Now you actually don't really need the absolute values because our population is always going to be positive, so I'm going to ignore that. Be very careful of this guy. This is going to be negative 1 over 500 natural log of 500 minus p. And again, the reason for this negative right here is because you'd have to undo the chain rule when you took the derivative of ln of 500 minus p. Okay, so now we've taken care of the differentiation part. I'm sorry, the integration part. Now we just got to work on some algebra here. So what I would do is I'm going to multiply both sides. I'm going to multiply both sides by 500. So if you multiply by 500, you end up getting ln of p minus ln of 500 minus p is equal to negative 0.4 or positive 0.4 t plus c. And now what I'm going to do is, for reasons that will only make sense a few steps after this, I'm actually going to factor out a negative, or I'm going to multiply both sides by -1 to make it look like this. When you multiply both sides by a negative, it turns this into a negative 0.4. And then the c can absorb the negative, so I'll just call that plus c. And then I'm going to use a property of logs and call this 500 minus p over p equals negative 0.4 t plus c. Now I use the definition of ln. So this is e to the, so 500 minus p over p equals e to the negative 0.4 t plus c. Which I can write as e to the negative 0.4 t times e to the c, and I can call that an a. So I can call this a e to the negative 0.4 t. And so now I can write this as 500 over p minus p over p, which is 1, and that equals a e to the negative 0.4 t. I'm going to add 1 to both sides, so I get 500 over p equals 1 plus a e to the negative 0.4 t. And then when you cross multiply, again we're trying to solve for p. If you cross multiply and divide, you get p equals 500 divided by 1 plus a e to the negative 0.4 t. So we're actually almost done. We just need to use our initial condition there. So I've basically the steps of her solving all logistics are going to look just like this. You'll have a different carrying capacity. But to find our A, we need to use the initial condition, which is that the initial population was 40. So P of 0 equals 40 would imply that 500 over 1 plus A e to the negative 0.4 times 0 is just 1. So that I'm just leave that as 1 plus A. That is supposed to equal to 40. And if you solve for A, that means that A equals 11.5. So I'll ignore the details of that. You can solve that equation. A is 11.5. And so now our final solution is this one. So there's the solution to that differential equation. So a couple things to note. First of all, the carrying capacity is there in the numerator. That's the carrying capacity. Your initial value, or that A, was determined by the initial condition. But the other thing is, I don't think this is not really one of the differential equations that you'd be responsible for solving on the AP exam, because it just takes too long. There's too many places to mess up. There are other differential equations they'd expect you to solve. But just to summarize, if you have a logistic, in general, if you have logistic logistic growth, the differential equation will look like this. The solution will always look like this. All right. So if you tracked the m's and the k's and the in what we just did up here, you'd find that that's the general solution. Or you could just replace the numbers with k's and m's and do exactly what we did up here, and you'd find that this is the case. All right. So, but again, the more important part is to be able to analyze the differential equation. Finally, we'll just finish with what the limit is. The limit as t goes to infinity would be the limit as t goes to infinity of our guy there, which is 500 over 1 plus 11.5 e to the negative 0.4t. And you'll notice that this, as t goes to infinity, this goes to 0 because that's really like 11.5 divided by e to the positive 0.4t. And as t goes to infinity, that goes to 0. So this goes to 500, which is what we'd expect because in a logistic growth model, we would expect that as time goes to infinity, your population should approach the carrying capacity. So this all checks out with our intuitions. So that wraps up logistic growth models.